So we've finished the first three representations, the impulse response, connection vectors, and the polynomial representation. And now we go into the last three. And the last three are really important for understanding how our decoder works. So using this representation of the encoder leads us to the implementation of the decoder. So the implementation of an encoder is simple. It's this shift register, very, very simple, very cost effective. Now, for the decoder, things get much, much trickier. So the first concept that's very important to understand about convolutional encoding is the interpretation of the encoder as a finite state machine. So when I talk about a finite state machine, what's the definition of a finite state machine? The output at a certain time is a function of the contents of the registers. And we call that the state of the registers, which is why we have this word state here and state here. So the state of the registers essentially determines what the output is going to be. So the encoding process you can think of as being a transition from one state to another state. So we're going to think about the encoder stepping through different states based on looking at what are the entries of the shift register. Of course, the number of shift registers is finite, which is why we have a finite state machine. So we'll start with what we call a state diagram for a finite state machine. And surprise, surprise, it's related to this vector representation of the encoder. And this is going to be the finite state machine. And I'm going to build it for you so you can understand how we ended up here, how these things related. So we'll start in the first step. When we build a state diagram, a finite state machine, we're looking at this idea of having a state and then an input buffer. So the state in this example that we've been doing is 2 because the number of registers, K, is the constraint length, and it is equal to the number of registers. And in the registers, one of them is always the input buffer, which means that 2 to the k minus 1 is the number of states, because k minus 1 are the number of registers in the state. So in our example, the constraint length is 3 because we have 3 registers. The first register is the input buffer, which means we have k minus 1, in this case 2, which are the number of registers dedicated to the state of the state machine. Now, because we're doing binary, those states could be 0, 0, 0, 1, 1, 0, 1, or 1, 1. So there are 2 to the k minus 1 states in a binary. Of course, if small k were bigger than that, then the number of states would be larger. But this is for the binary case we're examining. So now we know how big, how many states are there? Well, there's 4 in our example. So I have 4 boxes because I have 4 states. So that's the first part of building the state diagram. Next, I say, well, each one of those states, what am I going to label them? Well, I'm going to label them with what the possible values are at that state. For instance, it could be 0, 0, and I'm going to call that state A. The 2 registers could be 0, 1, I'll call that state C, 1, 0, state B, and finally 1, 1 will be state D. So there are 4 states. I could call them A, B, C, D. I could call them 0, 0, 0, 1, 0, but they're just names. They're just states. So it's an abstraction of the mathematics that's going on behind it. Now, the next step is to establish valid transitions. Now, I have a shift register, which means I shift things in. So that means that the next state cannot just be random, right? The next state, in this case, this one is going to shift over to that one. So for sure, there's a structure that is due to the fact that I have a shift register. And that is what we see on these transitions from one state to the next. Now I have a binary input, which means that there could be two inputs that determine the next state. So going back again, here I have my input buffer. If the input has a 0, when I shift everything, it'll be a 0 that moves into this position. If my input is a 1, then it'll be a 1 that moves into the first the register in the state. So the input can be binary. So that means there's two binary transitions which are possible for each one, for each instant of time. So I'm going to use solid lines to represent what happens when the input bit was a 0, and I'm going to use dashed lines to represent what happens when the input bit is a 1. So let's look at what these transitions could be. For instance, let me take an example. Certainly if I'm at 0, 0, and that my input buffer is another 0, when I shift, I'm going to get 0, 0 again, which is why what we see here is we circle right back. If I'm at state A and I input a 0, I'm going to get the state again. So what happens when I'm at 1, 1? So my registers are 1, 1. My input here, let's say it's a 0 again. So when it shifts, I'm going to get a 0, 1. So that means when I see the input of a 0 bit now, what I'm doing is I'm looking here, and now this is the transition. I'm going to go from D, this is state D, and this is state C. So what I do is I look at just the shift register, and I say there are certain valid transitions with this arrangement of shift registers. And so this is pretty standard. I haven't really assigned a code to it yet. This is just the number of registers. This is just the constraint length. Gives me all of this diagram. The constraint length tells me, oh, I'm going to have to build a diagram and it's going to look like this. So the next part is to actually introduce the code. So the structure of the state diagram determined just by the constraint length. But now I have a specific code that I'm interested in. So I have a vector or a collection of vectors which represent the code. Now what I do is I write next to each one of these valid transitions, next to each valid transition, I'm going to write what is the code word that is involved in that transition. Remember, if I have a transition, let's say the transition from A to B, A transiting to B. That means, I know what that means. That means that I was at 0, 0, and the transition to B is a dotted line, so that's a 1. So I know the 3 registers. If I know the 3 registers, then I can calculate what is the code word. Well, it's 1 plus 0 plus 0, that gives me a 1, and it's a 1 plus 0 plus 0, it gives me 1, 1, poof, which is what I see here. Right next to this transition from A to B, I wrote what the output of the encoder would be. So I do that for every single transition on this state diagram. I just do the math, and I figure out for that transition what's inside the registers. Based on what's inside the registers, what is the code word that's generated. So I populate this state diagram with the output for this particular code. So that's what changes from one code to the next, is what I'm writing next to each one of these transitions. Now we're going to return to our original example, and we're going to see what happens. Well, let's say, for instance, that we're starting at state 1, 0, and that we're going to put in something. So that means we're starting at state B. 1, 0 here, that means state B. So I'm starting at state B just for example. And the next state is 0. Let's say I shift in a 0. Well, I look here, that's the transition with a solid line, and I see that if I have the solid line, I go from B to C. So I follow through that. I know that the next state will be 0, 1, because I just take that 0, I shift it, and then this 1 gets shifted, and I know I'm going to have a 0, 1. Now the output from this transition would be 1, 0. So that's what's written here, 1, 0. This transition outputs 1, 0. How did I get that 1, 0? Well, it's because I took register 1, 2, and 3. 1, 2, and 3, added them up, and I got a 1. And for the second code bit, I took register 1 and register 3, these two zeros, and that gave me a 0. So again, this is how I populated that. But instead of doing the calculation every time, I just know whenever I go from B to C, that outputs a 1, 0. So I don't have to go through all the math. I just need this register, this finite state machine representation in order to do the encoding. So it's less complex. This is a table that you find in your textbook that shows the encoding of a message. And I just want to show you how you can interpret this table, which is static, and to try and look at it in terms of what's going on dynamically inside of the finite state machine. So for instance, we're starting at the initial state of 0. So remember, you have to initialize it. So I'm assuming that my registers are initialized at 0. And then I input a 1. I shift in a 1. So if I shift in a 1, that means I'm going on the dotted line. I see the blue dotted line there. I'm going from A to state B. Along the way, when I'm doing this transition, I look outside and it's generating a 1, 1. Okay, so now I'm at state B. And what happens in state B, I input the next code word, the next message bit. In this case, it's a 1. So I look at the transition, and I see that on that transition, the code word that would be output would be a 0, 1. So there I see the output of my encoder, 0, 1. And of course, I'm going from state B to state D. So you can see in the table, he's just listing the states one after the other. Now the next bit input is a 0. Again, I'm looking for the solid line transition, and that takes me from D to state C, and the output along the way is a 0, 1. So I can continue to step through the encoding of this sequence of data bits. So now I'm to state C. From state C, I input a 1. I go along the dotted line to state B. Along the way, I'm outputting a 0, 0 as the code word. Now I'm at state B. I shift in my new word, which is my new bit. My data bit is a 1, so I follow the dotted line, which takes me from B to D. And along the way, I see that the code word output is 0, 1. And from there, I've got my sequence here, output. So this is a little longer example of a longer message sequence, and this is the coded output sequence that I get out of my decoder. So we can see that, looking at this table, it's kind of hard to see what's going on, but when we look at the state machine, the finite state machine, it's very clear how we're moving around, and the calculation is really just a lookup table about what the code words are for different transitions. So this was nice, but I had to stand here and step you through this. Suppose I wanted you to be able to visualize at once this flow in time, sort of like a graph versus time. How would I do that? And so that brings us to one of the next representation of the finite state machine, and that is a tree diagram. So a tree diagram, I can find a way of visualizing what's going on as time goes on. So it has the same principles as the state diagram, and really it's another state diagram, but this state diagram, instead of being something that turns in on itself, is one that develops with time. So we have to start somewhere, and you can see there are labels here about what the state is. So I'm assuming that we start at state A, which is start with the registers set to 0. And then here, if I start at A, there's a transition that goes back to A, and there's a transition that goes to B. So in the tree diagram, there's down, which is when a 1 occurs, and I use up for when a 0 occurs. So input bit 0, go up, input bit 1, go down. So if an input is 0, I go up, well I have to stay at A, at the same state, but if I go down, I go to B. So I get this. So now I have two possibilities, state A or state B. Just like in this case, if I'm at A, then I can stay at A, or I can go to B. So I know what I'm going to do. Every time I have an A, I'm going to branch between A and B. Now what happens when I have a B? Well, I could go to C, or I can go to D. So in my tree diagram, here I am at B, and if I get a 1 bit, then I'm going down to D. If I get a 0 bit, then I go up, and that's C. And when I have these transitions, just like before, Next to the transitions between B to C, there's this code word, 10. So again, in the transition between B and C, I again write the 10. So you can see here, when I'm at A, I go up to A, down to B, just like I did here. Up to A, down to B, 0, 0, or 1, 1. Here it is again, 0, 0, or 1, 1. And I build my tree in that way. And of course, it's getting denser and denser and denser as time goes by. But you can see that it's basically the same information as here, same quantity of information. It's just representing it in another way. Why? So that we can track the behavior in time. So let's take the same example, which I stepped through with you for the finite state machine. And now I'm going to step through it with you for the tree diagram. So the first bit, first of all, I started A, assumption I started state A, and the first input bit was a 1. Remember, 1, go down. So I go down, and when I go down, the output is state 1, 1 here, and the state is B. The next bit is 1, so again, I go down. The next bit is a 0, so now I branch up in this tree. The next transition is a 1, I go down again. Another 1, I go down again. And now I can look back, and I have traced through here all of my transitions, and I can go back and say, well, at each transition, what was the code word? So the first transition gave me code word 1, 1. The second transition gave me code word 1, 0. The third transition gave me code word 0, 1. The next one gave code word 0, 0. And the one after that gave code word 0, 1. I kind of ran out of space here, so we stopped our, but we could keep going in this manner. And so now I have a way of tracing through time. Geez, that looked good, except, I don't have enough paper. I don't have enough real estate. So is there another way that we can get this nice flow of time, but in a compact way, so I don't have to go through this exponential growth in the number of elements in my diagram? And there is indeed a way of doing that. So far we've seen finite state machine, or we've taken that finite state machine and written in a tree hierarchy. So just to show, again, the parallels, before I would step through, and now I'm tracing through here. It's the exact same manipulations. Okay, so now, what are we going to do with this tree? How am I going to make it more practical? And the way I'm going to make it more practical is doing something called a trellis. Trellis versus a tree. I don't know if you're familiar with the word trellis, what it is exactly, but it is, like I have one in my garden, a nice trellis, and it's got a lattice on it, like this. And then on this lattice, I, grow flowers. And this trellis is, if I look at any point in it, it's very structured, really repeats itself. And that is what we're going to do. We're going to build a trellis as a way of representing what is essentially the same information that was in the tree structure. But the trellis is, of course, more compact. But even more importantly, it's the trellis that lets us see what's going on in a decoder. So let's really get a good look at what is a trellis and how do we represent the finite state machine with the trellis. So here is a trellis for the encoder that we have been examining so far. And we can see, first of all, the first part of the trellis is a list of states. So each one of these points represent the state in the finite state machine. In our case, there are 4 states, A, B, C, and D. And of course, we have different transitions that can happen. So these would be our valid transitions, either 1 with a solid line, 0 with a solid line, or 1 with a dotted line. And as I look at these transitions, just like I had before in my finite state machine, valid transitions, next to each one of the valid transitions, I write the code word that comes out from that transition. For instance, there's a transition from A to A, stays here in the same state, and the output then would be 0, 0. So this representation is a way where we can take the information, which is about a transition from A to A to B. And my tree, I was like constantly repeating it, but also expanding out. Here, I take this compact form where I have all the information, all of the valid transitions, all of the code words next to the valid transitions, and I just repeat it, tile it, one after the other. And that's how I build my trellis. So take those transitions, write them out once, and then just tile them one after the other. So let's take this trellis and see how we can take our data, which is listed here, and push it through this trellis and see how we can represent what happens going through this trellis. So this will be my data input. Down here I'll keep track of my data output. So the first thing I do is I start at state A and I input a 1. Great, that's the dotted line. I go from A to B and the output is 1, 1, the code word. Now I'm at state B and the next bit that comes in is a 1. So I go from state B to state D. Along the way I output code word 0, 1. Up here at the top I'm also keeping track as a function of time what data I'm putting in. So what I'm pointing to here, I'm just repeating it at the top here. So third data bit is a 0, and so I do the transition on the solid line. I go from state D to state C. Along the way I output code word 0, 1. I'm at state C. I now have an input of 1. So I follow the dotted line and that takes me from to state B, and along the way I output code word 0, 0. I'm at state B. The next bit in is a 1, and now I transition down to state D and output the last code word along the way. So what's great about a trellis is I can see the development with time. I can see a path through the trellis that represents this stream of data that was encoded. The path is just the sequence. This sequence determines the path. So this is the path, this data, this path. When I have a path, you show me a path, I'll tell you what the data is. I see a path that has dotted, oh, that means it was a 1. I see a path, oh, that part is dotted, that was a 1. This is the solid part, that was a 0. And so what we're going to see is that this representation of the path easily gives me what was the data. There's like a 1-to-1 correspondence between a path and the data that was sent.